Hello students, we're now beginning to study the mechanics and processing of steel materials, focusing primarily on 5 aspects. The first aspect is the tensile strength of steel materials. The second is the impact toughness of steel materials. The third is hardness. The fourth is fatigue resistance, and the final one is the processing performance of steel materials. The tensile strength of steel materials is its primary performance and is extremely important in our current reinforced concrete structures and other constructions. When steel materials are subjected to tension, they not only generate stress but also produce corresponding strain. The relationship between stress and strain reflects the fundamental mechanical characteristic, often referred to as Hooke's law. The primary method for determining the tensile strength of steel materials is our tensile testing experiment. The following figure is the stress-strain relationship of mild steel can be seen. Mild steel from being pulled off experience the main 4 stages, but also in the process of tensile experience of steel we usually see 4 stages. The first is the elasticity stage, the second is the use stage, the third is the strengthening stage. Mild steel from the tensile to be pulled off the 4 stages, it is characterized by the performance of different, where in the process of structural design, some of the required performance indicators are very much related to the tensile steel bar. First of all, in the elastic stage, it refers to the stress and strain is proportional to the unloading of the specimen will be restored to its original state, manifested as elastic deformation. The use stage is characterized by the rate of strain increase being greater than the rate of stress growth. Stress and strain are no longer proportional, leading to the initiation of plastic deformation. In the strengthening stage, when the load passes the yield point, changes occurred in the internal structure of the specimen, which results in an improved resistance to deformation. The final stage is necking stage, where after reaching the peak of strengthening, the cross-sectional area at the weakest point significantly reduces and then fracture occurs. Throughout the entire process of stretching the steel bar, you can observe changes in stress. It undergoes an initial increase, followed by decrease, and eventually reaches its highest value. Then we heard a boom and it was a breakage of steel rebar. Tensile properties are usually expressed in terms of the productivity of the steel bar, used to express the plastic properties of the steel bar index. We typically use the elongation at break, usually referred to as the percentage of elongation at break, to indicate plasticity. The greater the elongation at break, the better the plasticity, making it easier for various types of steel to be processed and ensuring the safe use of steel in construction. In many cases, especially with original carbon steel, we perform code drawing in engineering projects. This helps to enhance the strength and impact toughness of steel material. The impact toughness of steel materials refers to their ability to resist impact loads. It is measured by the energy absorption during fracture under impact loads, often expressed as the absorbed energy in the notch condition. We use the term impact toughness as an indicator of this property, which is influenced by several factors. The first aspect to consider is the chemical composition of steel. When steel contains higher levels of harmful elements such as phosphorus and sulfur, its impact toughness decreases, which adversely affects its overall quality during smelting. For instance, incomplete deoxidation can lead to segregation, resulting in reduced impact toughness. Additionally, cold working and aging processes can also slightly diminish the impact toughness of steel. Environmental factors, particularly temperature, plays a significant role in this regard. When the ambient temperature drops below a certain threshold, steel's toughness experiences a substantial decline. This brittle fracture phenomenon in steel is commonly known as cold embrittlement. The third aspect concerns hardness, which measures a material's ability to resist localized deformation when subjected to pressure from a hard object. Depending on the testing method and range, hardness can be categorized as Brinell hardness, Rockwell hardness, Vickers hardness, Shore hardness, micro hardness, and high-temperature hardness. In construction steel, Brinell hardness (HB) is typically employed as one of the testing methods. The fourth aspect related to fatigue resistance. Fatigue damage is a phenomenon observed in engineering structures where steel can undergo sudden brittle fractures when subjected to repeated alternating loads, provided the stress remains below its yield strength. This type of damage is referred to as fatigue damage. The critical stress level for steel damage is expressed as the fatigue limit, determined through fatigue testing. It represents the maximum stress a specimen can withstand without experiencing fracture within a specified number of load cycles. The fifth aspect encompasses various process properties of steel. First and foremost, there is the cold bending property, which measures steel's ability to endure bending deformation at room temperature. Typically, this is expressed in terms of bending angle and bending diameter. In construction projects like bridges and buildings, steel bars are often bent into various shapes, demonstrating their cold bending performance. Another crucial property is the welding performance of steel bar, which refers to their ability to resist cracking and avoid a hard, brittle tendency under specific welding conditions. After welding, the mechanical properties of steel should not fall below the strength of the original material. The welding performance of steel plays a vital role in modern steel structures. Alright, it concludes this session here. Thank you everyone.